we'd like to bring to the stage Atmo from Berkeley, California.
Good afternoon, everyone. Okay, before we start, there's something I want to put in your mind. Today, there are only 5 organizations in the world that have a global and very accurate weather forecasting. All the other countries in the world are basically struggling to get very accurate weather forecasts. So I'm Johan Mate, and I'm the CTO and co-founder at Atmo. All right. So let's start by looking at a few supercomputers, especially their price. So let's start with Europe. This supercomputer is 130 million of OPEX per year to operate. This is the one at the Met Office. This is 1 billion CapEx, 2,000 permanent staff. And finally, the biggest systems of all, the one in the US. We're reaching $3 billion of CapEx here. So this is for the pricing. Now, there's another aspect of weather forecasting, and that's complexity. So in order to run these systems, you need a whole laundry list of operators. You need Fortran experts, Linux kernel experts, cooling experts. You need people who know their way around power. This sucks a lot of power. You need sysadmins. Meanwhile, the only thing that, or the main thing that people want to do in organizations like NOAA and others is to predict the weather and work on climate models. There's another thing, and it's technical debt. So these systems work with technologies from the 60s, mostly. Supercomputers in weather were one of the initial use cases. So we're talking about Fortran, MPI, and today, it's still the same technical stack that's running in this system mostly. Meanwhile, a lot of the innovations on the data science front, all the new generation of data scientists and scientists coming, might have some knowledge of Fortran, but they mostly work with tools like Python, Jupyter, Julia, and so on and so forth. So one of the things that we're doing at Atmo, and I'll dig a little bit more into that, is to break this barrier between these two technological stacks. So let's take a step back. Weather forecasting price and complexity make it impossible for most of the countries today to run their own weather forecast. That's a big deal. Once you realize that, it's critical for climate adaptation and for a whole range of economical issues. So our answer to that is the Atmo Kelvin. This is a fully integrated system that does software and hardware to answer all these problems. So what have we built? We've built a system that is data-centerless, so that means that it contains the cooling, the power, all the network is already installed in the system. And that is very important for countries that do not have access yet to facilities like data centers. And we've also built a hybrid AI NWP system, meaning that basically to reduce the cost, we accelerate NWP using modern techniques like deep learning and hyperparameter search. I'll go deeper into that later. So this is about like a survey of what we had to do to build the system. We've had to work on the software front, as I mentioned, basically bringing deep learning to the NWP stack. Building things like neural post-processing, that's in the family of model output statistics. We've built neural parameterization, meaning that we replace some of the batteries, I will call them batteries, of the NWP stack with deep learning. We've improved visualization through various techniques, especially photorealistic weather visualization in 3D. We've built visualization systems on web interfaces. And we can explore up to 21 million models, weather models, to see which one is going to be best for a specific area automatically. We go up to 2x the accuracy of a regular model without human intervention, meaning that the work of a modern forecaster will be to sometimes try a different model, so we automate this whole process. And one thing also, obviously, to understand behind this is that this is very data hungry. We collect a lot of weather data, either from all the various sources, weather stations, satellites, and so on and so forth. And obviously, we rest on the shoulders of giants. We use a lot of NASA data for that. Among the various sources, we use GPM for our rain ground truth. We use MODIS for the various terrain, NASAM for elevation, goes for the satellites, and so on and so forth. So thank you for that. This is one of the visualization techniques that we have. So what you would expect today, basically go in a browser and have good renderings of in that case, that's rain. We also have implemented a few protocols for direct delivery of alerts. That's especially useful for extreme events, especially in countries where the impact of delivering this right away is important. Some countries, in terms of their development, between the forecast of the weather and alerting the citizens, are really struggling. So we've had a lot of fun with this one. This is one of our employees that one day decided to, why not just do a 3D rendering? And so this is basically our weather forecasting that you can see, especially the clouds here are very obvious. And this allows us to actually compare hyperlocal weather forecasts in places that are critical, especially for infrastructure, like airports, ports, and at the level of a city. Okay, so how do we reduce the price of the forecast? So this is critical. The two technologies that I mentioned, that are neural parametrization and neural post-processing, allow to basically do super resolution with the forecast. So you can simulate at a slightly lower resolution, and that way break the cost. So that's one of the ways. And parametrization is also a big deal. So the parametrizations are these heuristics that are basically evaluating the interactions between the atmosphere and the rest of the system. And some of them, like microphysics or convection, are very, very costly, and they rely on heuristics. So you can actually replace these with machine learning techniques. Okay. So again, by reducing the complexity and the price of weather supercomputers, we make weather and climate forecasting and supercomputing available to every country. So how are we doing in terms of progress? Here what you can see is basically a Pelican case. It's hard to see on this slide, but this is the first version that's been built. So it's running daily, and it's forecasting the weather for East Africa. One thing that is also interesting with this form factor is that it can be shipped to anybody who is running operations. So that could be used for missions when you need to do a hyperlocal weather forecast, for instance, for defense purposes. The Atmo Kelvin 4 is designed. We are going to be delivering this one in Uganda in May 2022. This is a 1/10 build, so we wanted to see it on a small scale. In terms of business development, we've signed letter of intent with 21 countries in Africa. We have, as I mentioned, deployed the systems in Kenya, and our most advanced partnership is with Uganda, where we are going to be delivering the full-blown system in May 2022. Actually, a month ago, I was in Uganda signing the LOI with the director of the UNMAS, which is the meteorological agency there. And it was just great to see on the ground how the people were receiving the products. It was really the reactions were like, yes, this is what we need. We've wanted something like that for a while. We're also working with government contractors. An example here is Thales. So we have generated risk maps for drone flights. This is used basically for, as I mentioned, the drone trajectories, but also the source of the data is hyperlocal weather forecasting. We're running the forecasting at higher resolution, especially for things like turbulence and icing. And it took us only 6 months from first contact to the delivery with Thales to deliver this. Okay, so now our goal is to deliver the system to 5 countries within 2 years. How are we going to do that? Well, we've assembled a team of about 10 people now, and we think that's going to be key for deployment. So first, some of the past achievements of the founders and the executives. The main theme behind this is basically applying deep learning to physical sciences. So my co-founder, Alexander, was one of the co-founders of ATMO, one of the biggest deep learning companies for drug discovery. Some of our executives have worked at Apollo Fusion for delivering TRL-9 space propulsion Hall effect thrusters, optimizing some of the plume with machine learning and deep learning. We have alumni from Google X and Project Loon. That's actually where I learned about using the weather the first time. And we've delivered deep learning-enabled devices approved by the FDA at Caption Health. Our head of design designed 21 vehicles, among these some classics like the Mini Cooper and the Fiat 500. Our head of business development, that's her on the picture here. That's Anna. So she was in Iraq for about 8 years. She's been working with General Petraeus in Iraq. And so she has more than 25 years of experience in foreign services. A lot of employees from Google working in the early days of distributed file systems. And a very strong culture in applied math. We have some contributors to open source libraries in GeoMSAT, for instance, which is a cool product for doing Riemannian geometry. Okay, so before we close, I want to show you this map, which is basically the map of the countries that will be hit the worst by climate change. And if you look at, as I mentioned at the beginning, the 5 countries or the 5 organizations that have the best forecast today, these are the countries that are green on this map. And the countries that are red are the ones that are going to be hit the worst. When we started with Atmo, the mission was really how do we deliver something that can help all these countries and making a healthy business. Okay, long term, we see Atmo as a platform that's going to grow and become the reference for all atmospheric and climate modeling. Hence the name of the company, Atmo. We don't really see climate and weather being 2 separate things. We see that under the umbrella of atmospheric forecasting. And in terms of markets, we've done our evaluations, and this is about a 30 billion market. I'm happy to explain how we come to this conclusion in the roundtable. And the reason why I'm here today is to see how can Atmo benefit NASA or other various US agencies. As I mentioned, we started collaborating with countries all over the world, but we're really excited to deploy this technology in the US too. As it was mentioned at the beginning, we're located in Berkeley, California. So we're excited to talk to you. Thank you.